All right, so what I'm going to be discussing today is just like a real brief overview of essentially everything you learned in 293. Just a refresher on which analyses we talked about that fall into which category. You're going to need to have a functional knowledge of use for various analyses when an analysis is appropriate, to help you identify why we're doing the particular analyses we're doing for your project. So even though this is not a statistics focused course, you do need to have that working knowledge of various statistical analyses to understand research. So with statistics and research methods, you kind of can't have one without the other. So if we're talking statistics, statistics are just one tool in the toolbox of a scientist. If you want to have a sort of a systemic and quantifiable approach to learning about whatever phenomena you're interested in studying, statistics is just going to be one way to do that. It helps you describe your data. It helps you synthesize your data such that you can draw conclusions. It helps us understand things about the world, meaning whatever variable we're interested in. There may be an appropriate statistical analysis or outcome that helps shed light on something about that variable that you're interested in. So anything ranging from a simple average that tells you something about where most people are located on a scale, to how spread out scores are, to quantifying the strength with which variables are related. The two classes we learned about are your basic descriptive statistics that typically summarize something going on within a single variable, not all the time, but typically, and then inferential, which is what allows you to draw various conclusions. So I'm really just going to just quickly go through the basic statistics that we learned about in these two categories in 293. So when starting with descriptive statistics, this is your more basic organizing, summarizing, and describing your data. So if, for example, if you have categorical data, like what major is someone in, you want to be able to pull out some information that synthesizes something going on with that variable to help communicate and understand what's going on. So you would look at categorical data like this and say most people are psychology majors. Statistics can be as simple as that. If, though, you notice that another variable is numerical in nature, you might say to yourself, well, taking the mean or the median is going to be a lot more informative or useful in that context. So when you just want to really basically describe data, this is typically when you're trying to break down a single variable and orient yourself to something that's going on with that variable. Inferential statistics take it to the next level. This is when you want to make interpretations based on the data and actually draw some solid conclusions, typically by relating multiple variables together. So in order to do this, you're going to want to use your a priori hypothesis testing, which if you guys remember from 293, basically that's the theoretical framework that yields us our p-values. So there's typically not a p-value associated with your mean or your standard deviation, but there is with your Pearson's R, or with your F statistic from your ANOVA. So your various statistics are all about drawing conclusions about relationships between variables, but the variable type is what yields the different sorts of conclusions that you could make. And to a certain extent, the research methods that you use. Are you doing a correlational study that has quantitative variables that you're trying to link together? Or did you go through the rigmarole of doing a more rigorous experimental design that would enable you to make those more causal claims? No matter what sort of a claim you're trying to make, if you're trying to relate variables together, typically we're going to subject those analyses to our hypothesis testing. We want to test for statistical significance. So again, I'm just going to walk you through basically the spectrum of the real core analyses that we learned about in 293 so that you're sort of refreshed on them, because you're going to need to be able to use at least a handful of these when you're writing up the data that you'll be analyzing from your project. Within the realm of descriptive statistics, I'm going to talk about your frequency distributions and your scatter plots. You could also talk about any sort of graphical depiction, but for a frequency distribution and a scatter plot, it just keeps it a bit basic, but really any other sort of graphic you could find, pie chart, whatever, you could imagine that as sort of a subtype of a descriptive statistic. Your mean, median, and mode, your central tendency statistics, and variance and standard deviation. So in terms of which descriptive statistics you're going to more commonly see and which you will need to report in your paper, well, you're going to need a mean and a standard deviation, because if you remember anything about your 293 project or analyses that you read in academic articles, you'll notice that a lot of the time scales that have an average taken, you see the mean, standard deviation, and sometimes an internal reliability reported. Those you're going to need to be able to reproduce in your 294 paper, because those are some key bits of descriptive information that you need when you're writing up the results from your data. And something like a scatter plot or a frequency distribution, those are nice to have too. They're nice visual descriptions that help communicate something about your data. So if we're talking frequency distributions, this is just going to be a table or a figure, if you're creating a histogram, that depicts the frequency of various scores in your data set. So you might have a grouped frequency distribution when you have clusters of similar scores, and you're indicating the frequency with which your participants fell into any one of those intervals. If you're dealing with data that is on a somewhat large quantitative scale and lots of similar values that your participants gave you on that variable, a grouped frequency distribution synthesizes the data a bit better. Frequency distributions can be used with categorical variables because it just relies on counts of various levels of your variable. So how many psych majors did you have?
Early in the third quarter.
If you were to take your frequency data and turn it into a bar chart such that the bars depict those frequencies, the frequencies up on the y-axis and the actual frequencies depicted as bars along the x-axis, you have transformed your frequency distribution table into a type of figure that we call a histogram. It's just a different way to depict the same sort of data. So if you want to depict frequencies, any of these would be options for you. You could even take your data from your Likert scale and break it down into a frequency distribution. And then from there, the world can be yours. You can break your frequencies into percentages that you could then transform into a pie chart. You use cumulative percentages. There's many different options for how you can depict your data just when you're depicting frequencies. And it's a just really great basic way to, in a sort of a punchy way, help your reader visualize sort of what's going on with your distribution of scores. Scatter plots are neat. That is like the lamest statement anyone could ever make. Scatter plots are neat. They sure are. Scatter plots are figures that specifically depict data points where the placement along the x and y axis indicates placement along two variables. So for any particular point that you see on this scatter plot, the positioning along the x-axis tells you where somebody fell on variable x, where positioning on the y-axis tells you where they fall on this variable depicted here. So it's a great way to visually depict a correlation, because a correlation is the relationship between two variables. So a scatter plot shows all of your participants with their data point indicating their level of the x and y variable. So this lets you visually assess a correlation, and we love that. It's a great visually impactful way to communicate something about the strength and the direction of the correlation between your two variables. If your scatter plots, if your data points are doing that left to right upward slope, you've got a positive correlation, that's neat. If it's sloped downward from left to right, you've got a negative correlation. So it tells you something in a way that's very visually easy to understand. Even a zero correlation, the scatter plot, can give you that valuable information. So a scatter plot like this, which depicts no correlation whatsoever, that's still useful information to have. When you find that variables you predicted would be related just aren't, scatter plot is a great way to depict that failure to find a relationship. It's just a different option for depicting correlational type information. If you ever wanted to use the median or any sorts of percentiles, this breaks your participants up into their various groups of high, medium, and low, basically. you were to identify a median, it's going to be the point within your spread of scores whereby 50% of the scores live above that score and 50% live below. The median is often a really great tool for depicting a central tendency for a variable that may be quite skewed, because the median, as opposed to the mean, is a type of average that's not so pulled around by extreme outliers. So you often do see the median, as well as percentiles in general, being used to depict income brackets. Because as we know in the United States, income inequality is rampant, and so the existence of your trillionaires Jeff Bezos and his ilk are going to be pulling around what we consider the quote unquote average income if you were to just take the mean. The median, on the other hand, is not quite so skewed by that free show, Jeff Bezos. Trillionaires shouldn't exist. Just putting it out there. I don't care what anybody says. Okay, so then lastly, in terms of writing up your descriptive analyses, lastly, I'm going to touch on how you typically are going to write up a mean and a standard deviation. So just to show you how this often looks from a paper of my own, you guys are going to, once again this semester, be creating an average, in this case just for your dependent variable. But as such, you're going to need to include that basic descriptive information that is always necessary to include when you are taking the average of a set of items. So for any scale that is constituted by multiple similar items, you want to boil those questions down into a single average, whereby all your participants have a single score that indicates where they fall on that variable. So the basic information you want to include when you are using a scale in the context of your survey, a sample item, indicating the response format, you need all that information, but you also need your basic descriptive information to tell your readers something about the usefulness of that average. So to do that, you include the mean, the standard deviation, and your Cronbach's alpha for internal reliability. All of that information together tells the reader about sort of what your scale is about. It centralizes where people are generally located on that scale. It gives a sense of how spread out scores are on that scale. And the internal reliability, your Cronbach's over here, tells you about whether or not the items within the scale belong together. Internal reliability. If we're averaging a series of items from a scale and boiling it down to a single average, we want an indication that those items actually belong in the same group. Do they hang together? Do they correlate with one another? If you have a low internal reliability, it means that people are responding to the items in the scale in an inconsistent way. It sort of diminishes the usefulness of your scale by indicating that your reliability or consistency was garbage. So you want your Cronbach's alpha for internal reliability to assure your reader that your scale is functioning the way you want it to. So you're going to see this set of information for descriptive statistics very often reported together. You're going to need that information for your dependent variable in your paper for 294. Then moving on to the class of inferential statistics. Again, this is just going to be a brief walkthrough of the real core inferential stats that we did in 293. Any of your inferential tests should be subjected to significance testing. That means it should yield a p-value that tells you about whether or not your variables are truly related. And when I say related, that could mean an association type sense, as in you did a correlational analysis, or in a more causal sense, as you guys are doing with your experiment. But for any inferential statistics, they all can plug into this hypothesis testing framework, whereby you set a significance value that you want to hit, namely p equals 0.05 or less. And only if you hit that p-value, that critical probability threshold, do you declare that you have actually found the results you were predicting. So the real core ones we learned about in 293, we did a Pearson's R, fantastic. We did a couple kinds of t-tests. You might end up doing a t-test in the context of your 294 data. You likely could get away without doing a Pearson's R unless you maybe wanted to correlate your DV with age or something like that. You may be able to bypass a Pearson's R altogether. But if you want to assess the main effect of your experimental condition, your IV on your DV, you could start with a t-test. We're ultimately going to do a more complex factorial ANOVA as well. But since you've got an experimental group and a control group, That puts people into 2 independent samples, and you could just see whether or not there's a main effect of your IV on your DV using your good old independent samples t-test. Shouldn't be a need for a related samples t-test. You are not having all your participants experience all levels of the IV. And then for your ANOVA, kind of the fanciest statistic that we did in 293. It was kind of a beast. We are going to be doing a fancy ANOVA in 294, but we're not going to have to compute anything by hand. We're just going to be doing it in SPSS, but I want you guys to understand why we're doing an ANOVA. So I'm going to walk through just some examples of these core inferential tests. Again, hopefully, if you are still sort of fresh on what you learned in 293, most of you took it with me either over the summer or in the spring. So hopefully, this is all sort of just a refresher. Okay, so in terms of correlational analyses, again, a correlation is going to be a single numerical value that tells you about the strength of the association between 2 quantitative variables. Correlations do not tell you about causality because they are not the result of manipulating a variable, just measuring values of your 2 variables. So your correlational data would often look like this. This is that same example of a correlational matrix that I was always showing students to show you an example of what I think is a great depiction of correlational data. Right, the values here are your Pearson's R values. So for example, that 0.26 is the relationship between nostalgia, as indicated by the nostalgia row, to authenticity, as indicated by the fact that it is in the column labeled 2. So a correlation matrix like this, once you orient yourself to how the info is being presented, is just a really great, slick way to depict your correlational information. A neat legend that just flags significant correlations with a set of asterisks, that's great too. That way, you just have a lot of information communicated in a way that is both clear and concise. So if you do end up doing a correlation in the context of your 294 analyses and you like the results you get, this is a great way to depict them. I do recommend. When you're reading your SPSS output for your Pearson's R, again, it just looks like this. You get your variables named downwards and sideways, and if you were to look at the relationship in some of my fake data that I used in the correlation lecture between nostalgia and happiness, right, you get your Pearson's R there. You've got your p-value, your specific p-value, and you have it flagged for significance. So that's how your correlational output looks. Pretty easy. Again, you may not need to do a correlation in your data, although it's fun to try different things when you've got a cool new data set in your hand. So I encourage you to refresh yourself on how to do all these analyses, even if you don't write them up. Now, independent samples t-test, right? This is when you want to compare mean differences between 2 groups. So an example of this analysis from one of my old 293 lectures, where the hypothetical research question was whether or not a violent or a non-violent video game impacted, I don't even remember what this DV was, whatever, compares to mean differences. Okay, so then a t-test yields an obtained t-statistic and a significance value, and if you indicate that you want descriptives, you'll have the actual means. So this particular analysis yielded a non-significant t-statistic. You can tell because the t has a p-value that is greater than p equals 0.05. And you can look at the means and you can eyeball them and see which group was higher on your DV, even if it's non-significant, but always with the caveat that if something is non-significant, this difference might just be fluky. So I'm going to also show you some examples from publications of all these analyses that I'm referencing. So I found one study that utilized an independent samples t-test. It was a pretty cool study on the relationship between meaning in life and resilience in older adults. And one particular analysis was interested in demographic breakdown on their DVs of interest. So in the table, they show the mean scores of participants' resilience based on a variety of demographic characteristics. Now, a couple of the characteristics that they were looking at the differences in resilience on was gender. So if you guys remember from 293, I kept saying that a group differences test or analysis is going to depend on how many groups you have in your IV, and that gender, if it's broken down by just men versus women, it would be appropriate to do an independent samples t-test because it's breaking breaking your data down into 2 different groups. So what you see here is the results from the study of the difference between men and women on this resilience factor. So they found a significant relationship such that gender did impact this particular DV. You know that because they've got their T statistic presented and the p-value, which is less than p equals 0.05. Their first factor that they subjected to an independent samples t-test of marital status, it looked like it was like maybe in an interesting direction, but not particularly close to p equals 0.05. But the reason both of these variables, these demographic variables, are subjected to an independent samples t-test is because there were 2 groups. A related samples t-test, on the other hand, is going to be appropriate for any research design whereby you are not dealing with 2 independent groups, but your groups are related to one another. So this could either be a repeated measures design, whereby you're evaluating somebody's values on the DV from a time 1 and a time 2. So one of the examples I used for this in 293 was to look at performance on a 293 exam. So all students had taken exam 1 and then they took exam 2. And my question was whether or not students performed better on exam 1 or exam 2. So instead of just taking an independent samples t-test where I evaluated exam 1 separately from exam 2, I was interested in relating every student's performance to themselves. So did any single student have a better score at exam 2 versus their own personal time 1? So that's the difference between a related samples t-test and an independent samples t-test. If people are being compared to themselves, it is a related sample because it's a repeated measures design. So another article that I have here to indicate the appropriateness of a repeated measures design, anytime you have pre versus post testing evaluation. So this particular article was interested in traumatized adolescents scores on well-being outcomes pre and post therapeutic intervention. So the idea was whether or not any given person was better than how they were 3 months prior. So that's why it was a related samples t-test. Their results that you can see here, they did a whole host of repeated measures or related samples t-tests on anxiety, on depression, on PTSD, disassociation. Again, the idea is this was subjected to a related samples t-test because every individual is being compared to themselves. And you're obviously not independent from your own personal scores at time 1. Other examples of your related samples t-test would be something like a twin study where you're comparing a set of twins to one another, a marital study, so you're comparing husbands to wives, you're comparing siblings to each other. If it's a sample that's related to one another, a related samples t-test may be for you. You guys are almost certainly going to not need to do a related samples t-test for your 294 data because you are having your subjects randomly assigned to 2 independent groups. So now let's talk about your ANOVA. This is when things get a little bit more complicated, but this is definitely going to be something that you will be doing in your 294 analyses. So starting with your simpler ANOVA, a one-way ANOVA, as opposed to an independent samples t-test, is when you have a single independent variable and you want to look at its effect on a single DV, but you have more than 2 groups within that IV. So an independent samples t-test is not appropriate because you're comparing at least 3 groups of the IV to one another. So the example I used of this in 293, if the question is whether or not students are more stressed during summer vacation, in the middle of the semester, or during finals exam week, right, that breaks your sample down into 3 groups. Your single IV of time of the year has 3 levels or groups within it. That would mean that a one-way ANOVA is appropriate. A single IV that has 3+ levels within it. Okay, so in this case, you've got your means up here if you indicated you wanted descriptives for your ANOVA. So you can eyeball and check whether or not these groups are different from one another. But critically, you want to look down here at the bottom for your ANOVA F statistic and its significance value. So when you're reporting a one-way ANOVA, you definitely report your F statistic. You also report your degrees of freedom for between and within, within parentheses, and your p-value. Hopefully you remember, because I would never shut up about this anytime it came up. If you ever see 0.000 in your significance value, hopefully you all remember where I'm going with this. This does not mean your p-value is 0, because there is what? No such thing as p equals 0. There is never a 0% chance that you've made a mistake. Anytime you're breathing, it's possible you made a mistake. The only way to never be mistaken is to never say anything at all. There's no such thing as a p-value of 0. This is just SPSS going to the decimal places that it has available. If you see a sig value of 0.000, p is what? Less than 0.001. Never write p equals 0.000. I will take a point off on that. If I see that in your paper, I will take a point off. If I've said it so many times, you should know. Okay. So your F statistic, your sig value, degrees of freedom, these are all the key pieces of info you typically see reported when you have a one-way ANOVA. And actually that same study on resilience and meaning in life in older adults, it actually did some ANOVAs as well. Because not only did they subject their demographics that had 2 levels within them to a significance testing, they also used this education variable. So this education variable had people separated into much more than 2 groups, 1, 2, 3, 4, 5. So they wanted to compare those 5 groups to one another on this resilience outcome. So since there's more than 2 groups that is breaking down this IV of education, a one-way ANOVA is appropriate. And you'll notice they do not have a T statistic, they have an F statistic. Okay, so they've got the means for their various groups, they've got their F statistic, and they've got their significance value. So this tells you that there's a difference in resilience between these various educational groups. Now let's talk about a factorial ANOVA. So you guys in 294 will be doing a factorial ANOVA. You'll just be doing it in SPSS. So no hand calculations necessary, but you will be doing a factorial ANOVA. It's sort of the primary analysis from this particular project. So even though it's tricky, it is the most complicated analysis I'm covering today. You will be doing one, so try and get back into the zone you were in 293. So a factorial ANOVA is distinct from a one-way ANOVA in that it is an analysis to look at whether or not at least 2 IVs interact to impact the DV. So a one-way ANOVA is so called because it's the effect of one IV on your DV. Factorial is anytime there's 2+ IVs. So a 2-way ANOVA is where you have 2 IVs. A 3-way ANOVA would be where you have 3 IVs. Sky's the limit. But you guys will be doing a 2-way ANOVA in your analysis for 294, so a type of factorial ANOVA. So this example from 293, right, the effect of exercise, so light, heavy versus moderate exercise versus the time of day you got the exercise, and whether or not those 2 IVs interacted to impact sleep. So this is what your analyses, your output would look like for this kind of an ANOVA. Technically a 3x2. I know factorial notation is tricky, but recall that the factorial notation, the number of numbers indicates the number of IVs. So 3x2, there's a 3 and then there's a 2, standing for your 2 factors. 3, indicating this exercise IV that has 3 levels within it, by 2, the second IV that has 2 levels within it. Okay, so this is technically a 3x2 ANOVA on the DV of sleep. So then how do you actually read this monstrosity? You find your IVs separately. There's a row dedicated to the exercise IV and to the time IV. The F statistic and significance value in each of those rows is associated with what we call the main effect. So the main effect of exercise. There is a main effect of exercise intensity on sleep, as well as a main effect of time of exercise. Then this last row, exercise by time, that is the ANOVA that indicates whether or not the interaction was significant. So is there some combination of exercise intensity and time of day that uniquely impacts sleep, right? So does someone who gets heavy exercise in the evening have the best sleep, right? If there's some unique combination of your IVs where you see the highest level of the DV, that tells you that you may have an interaction. So this F and P value here is what tells you about the significance of your factorial ANOVA. Okay, so again, I know that this content can be very intimidating. You guys will be doing a 2x2 factorial ANOVA, or technically you could do a 2 by whatever, but you will be doing a factorial ANOVA where one of your IVs is your manipulated variable, and you're going to do a factorial ANOVA whereby you throw one of your demographic variables in as the second IV. So if, let's say, you want to look at the interaction of your manipulated variable and gender on your DV, right? Do women who experience the stress manipulation have the lowest level of happiness? That's what your 2x2 ANOVA can tell you. And I know it's complicated. We're going to be doing it in SPSS. An easy way to get a handle on what your factorial ANOVA tells you is don't just look at the results of the ANOVA, look at the means. See which of the means is different from all the other, broken down by the complete factorial combination of your IVs, and make a bar chart. Make a bar chart that depicts the mean levels of your happiness DV, broken down by women in the stress condition, women in the control, men in the stress, women in the control. And I can help you do all of this. Don't think you have to do all of this on your own. Okay, so then lastly, I'm going to show you an example of a factorial ANOVA in a publication. Okay, typically what you see when writing up or seeing written up a factorial ANOVA is you do see the notation indicated. So you'll see the notation broken down by both of the IVs and within parentheses, the levels of that IV. So in this particular article, a Terra Management article, the authors were interested in whether or not a death anxiety prime and age interacted to predict health promoting behaviors. So they broke down age into two groups, young adults versus older adults. You guys could do this too. I can show you how, it's pretty easy. By their manipulated variable, so they made some people feel anxious about their mortality and some people received a control condition. So the idea is they did a 2x2 design that they subjected to a 2x2 analysis of variance and ANOVA. So then this is what their analyses actually look like. They depicted the means using this line chart, right? So you can see that there does appear to be a difference between the means in those four groups, right? The complete combination of the death anxiety IV and the age IV. You could depict this as bars. That's perfectly fine too. Again, line versus bar chart is an aesthetic difference. This visual just tells you the various means in all four of those groups. Then for the actual write-up itself, right, again, they're going to write up the results of the ANOVA for your main effects, right? So did young adults versus older adults have higher health promoting behaviors even before you take death anxiety into account? So you're going to want to indicate your main effects. There will be an F and a P value for both of your main effects. And there's going to be a factorial ANOVA for the interaction between your two IVs and whether or not, in this case, age and death anxiety interact and uniquely affect health promoting behaviors when you take both IVs into account. So they indicate their notation, your 2x2 ANOVA. They indicate they report their results using their F statistics, degrees of freedom, and P values, and any main effects are reported on as well. So again, this is definitely the most advanced analysis we did in 293, so I know it might be intimidating. Again, take into account that we will be doing this in SPSS, and I'll be able to help you along the way, both in running these analyses and in interpretation. But that is the analysis that's going to sort of be the most important one from your project. So to help you walk back down memory lane in terms of understanding and finding statistics, we're going to do a lab activity that will be due tonight where you guys should just find one example of a descriptive stat and one example of an inferential stat. Find them on PsycInfo, and basically similar questions for finding your descriptive stat and your inferential stat. So find at least one descriptive statistic from the indicated list, the list that I walked through today, from a PsycInfo article. And what's the title? Give me the permalink. What was the descriptive? Was it a mean and standard deviation? Was it a frequency distribution? Was it a histogram? What variable was it depicting? If there's an image, show me. I would love to see it. And then say something briefly about what the statistic was communicating. Was it communicating frequencies? Was it communicating central tendency, variability? Say something about why the statistic is there. Then for your inferential stat, you're going to need to find one example of that, again from PsycInfo, article title permalink. And I know some of you are still playing and not giving me permalinks, you're giving me the URL. Don't do that, please. Find the permalink. It's in the right-hand toolbar. When you get to your PsycInfo article, go to the right-hand toolbar, click permalink. Towards the top of the page, the permalink will be generated in a little box towards the top of the page. Use that. Otherwise, it's a pain in the ass for me to see what article you found. So then indicate which inferential test was it. Was it a Pearson's R? Was it a t-test? Was it an ANOVA? What numerical information was concluded? So if it was a Pearson's R, right, you're typically going to see an R value, degrees of freedom, p-value, graphical depictions of the analysis. So like how there was a line chart for that last two-way ANOVA article I showed you. And then any conclusions drawn from the analysis. Was it significant? If so, what is the takeaway from that significant analysis? Okay, so that'll be due tonight. Then lastly, I'm going to touch on SPSS and VPN. So I know a lot of you are in 293 and you've been through this process. So hopefully you still have SPSS on whatever device you're using. If not, you're just going to want to re-download them. If you have not been in 293 with me and have not used SPSS before, basically you're going to need to go to the links here that are from the Miami bookstore. If you're on Windows, use these two links here. If you're using a Mac, use these links here. If you are not on campus, which I presume most of you are not, you are going to need to use Miami's VPN or virtual private network to be able to access SPSS. The reason is because Miami's purchased license for IBM SPSS statistics is only technically for on-campus usage. So if you use SPSS off campus, you will get a notification that you don't have the appropriate license. The VPN enables you to bypass this geographical restriction. I don't even really totally know what a VPN is. I know it's for some measure of like confidentiality, anonymity, security, whatever. All I know is in this context, the VPN is critical to being able to use SPSS off campus. An important thing to note is that the VPN is its own download. You then need to save that application to your desktop and you need to open it, and it should prompt you to log in with your Miami credentials. At that exact moment that you do that, have your phone with your Duo mobile app ready to go, because you will get a push notification simultaneously to your Duo mobile app that you will need to approve before the VPN is working. 99% of the time, if I've been talking to a student who says they can't get on SPSS because it says the license isn't right, it's because the VPN was not properly working. So getting that VPN right will be critical to using SPSS if you're not on campus, which I hope most of you aren't. Are they really going to send you guys back to campus? That sounds crazy to me. I don't know. Tell me how you guys feel about that. I would love to know your opinion on the absolute shitstorm that's about to happen. I won't be there, so I don't know. That does it for stats review. I know there was kind of a lot because basically it was a walk through 293 in its entirety, but I wanted to make sure you had that refresher materials to refer to so that you know kind of what analyses we'll be doing and why, and to help you revisit when different analyses are appropriate, which even though this is not a statistics course, the skill of being able to identify when various analyses are appropriate is a critical skill for a researcher to use. So that's why statistics is sort of part of research methods, just like research methods is an important part of statistics. You kind of can't have one without the other, so they do somewhat go together. So hopefully that helped. If you have any questions, let me know. At this point, I will cease the recording and take any questions that you guys might have.